Hello everybody and welcome to another class of ATMO 412. Last time we talked about extratropical cyclones and we delved a little bit into the dynamics of these systems, and we examined these systems from different points of view: potential vorticity, pressure, QG, and vorticity. Today we want to talk about another very important component of synoptic meteorology, and these are fronts. Fronts are to some degree a part of extratropical cyclones, although they're not exactly the same thing. Fronts are fronts and cyclones are cyclones, but they're important components, and so it's really important to try and understand what they are and how they evolve in time. First of all, like for everything, we must start by asking ourselves, what is a front? This is a complicated question because we talked about this time and again in this course. Whenever we talk about complex phenomena, like everything that happens in the atmosphere, it's really hard to provide a particular definition. There really is no universally accepted definition. All the definitions we can come up with, they manage to encapsulate, to capture some of the features of the fronts, but they don't capture all the features. They don't capture all the fronts. And much like with people, there are just too much diversity to apply labels, let's say, that are rigid and strict. And nevertheless, it is still useful to think about some operational definition just so that we know what we're talking about, because otherwise it's going to be chaos. Generally speaking, whenever we talk about fronts, we always mean an area of gradients, and particularly an area of strong temperature gradients. And maybe you could think of fronts as boundaries between different air masses. So for example, marine air masses versus continental dry air masses, or tropical versus polar air. And fronts are important for a variety of reasons. And by the way, I should say fronts also vary throughout the day. So we do see fronts on a map, but fronts are by no means static. So the diversity that we observe in fronts, we not only do we observe that in the population of fronts, but also in the life cycle of a single front. And even in the matter of a few hours, fronts can vary a lot in their behavior. Fronts matter because they influence the weather in the mid-latitudes a lot. They cause a lot of rainfall, and they cause different kinds of precipitation depending on where they happen and when they happen, and so forth. On the mainland, in the US, in the United States, fronts are often responsible for, during summertime, for the generation of pretty severe thunderstorms, so supercell storms and mesoscale and things like squall lines, for example. Fronts are really, really important. And fronts don't only exist near the surface, but they also exist aloft. And so fronts are also important for aviation meteorology. So pilots also care about fronts. And fronts are a bit of a wild animal in the sense that they have different scales. Okay, we'll see a front on a map in a few minutes, and you will see that fronts are really, really wide and often cover the entire United States, or substantial parts of it. And so their width has length scale of the order of 1,000 kilometers, so we're well into the synoptic scale. But the front itself, the direction across the front, the direction, the size of the temperature gradient, okay, the spatial, what am I looking for? The spatial extent of the temperature gradient is often pretty small, and is often of the order of 100 kilometers, more or less, because otherwise it wouldn't be a front, right, if it was a really wide temperature gradient. And so in a sense, I think it was Howie Bluestein, who said that fronts are, suggested that fronts are, in a sense, both mesoscale and synoptic scale features and belong to both worlds, in a sense, which also underscore the complexity and, again, the very wide diversity of phenomena that happen in the atmosphere. Among other things, this suggests that QG is not a valid framework to examine all the aspects of the front, because if we look along the front, then the length scale of the front in the width of the front is the length scale of synoptic systems. So 1,000 kilometers, Rossby radius is small, we're cool. But when we then consider the direction across the front, which is, to be honest, the most important, the most interesting, I would say, direction, then in that case, the length scale is 1 order of magnitude smaller. So that means that the Rossby radius is 1 order of magnitude larger, and so that means QG is not good there. What are the general characteristics that we observe on a front? And this is a synthesis of some of the characteristics that we hold as important, but it's not exhaustive, and not all the fronts have necessarily these characteristics. So to begin with, horizontal temperature contrasts. And right off the bat, this is not always true, because there are such things as dry lines, and dry lines are lines that separates air masses with different humidity. And this matters because the buoyancy is different, and so these are still bona fide fronts, and they can still have an impact on the weather. And in fact, dry lines initiate a lot of severe weather in particularly in the south of the United States. But temperature contrasts are more common, the most common features that we find in fronts. Often we find a minimum of pressure and a maximum of cyclonic vorticity along the front. We do see pretty significant wind shear, and we also observe horizontal wind shifts. We do observe large static stability within the frontal zone. We have ascending air typically near the front, and we tend to have precipitation and clouds, and that's the main reason why we care so much about fronts. And one of the generic features of most fronts is that they are most intense near the surface. Careful here, because fronts can also exist at higher altitudes, and this results in clear air turbulence. And so, the last point wouldn't apply to them, but by and large, most fronts that we understand, that we observe, are confined close to the surface. Okay. What do fronts look like? This is an analysis of a front from November 17, 2009, and this plot on the top left is showing sea level pressure with some subjective frontal analysis. These cold blue line with these triangles, this is a cold front, and the red line with these semicircle features, this is a warm front. And here we have similar thing, but we also have equivalent potential temperature contours. You can think of these as isotropes by and large. And 2 Kelvin spacing between these lines. And here we want to pay attention to the fact that notice how these lines are packed together. So there's a really, really strong gradient. I want to say, what state is that? Let's see. This is east of Oklahoma. That's like Illinois, Missouri, I want to say. South Illinois. And below Illinois is Louisiana, I want to say. So west of Louisiana, is it Louisiana? No, it's something else. Sorry, this is really embarrassing. Okay, well, west of Louisiana, east of Texas, there is a really strong gradient. You can see how many isotopes are packed together over here, and something also happens here, like here on the warm front. I will not attempt to identify those states because otherwise this lecture would take far too long. But over here, there's also a lot of tightly packed isotopes, not as strong as these ones, but still pretty decent. And over here, still same sea level pressure, and this is relative vorticity at 950 hectopascal. So, earlier we were saying vorticity maxima associated with fronts. There's a really nice cold front. Obviously, this is a cyclone that's developing, and so we expect vorticity here, but notice that, this front is also pretty generous with vorticity. And this is a cross-section, the last one over here, and it shows wind barbs and potential temperature isotopes. And you also observe, you do observe this frontal feature over here, but importantly, you tend to see here the wind shift that we were talking about earlier. Okay, so let's start to talk about the features of the front. And we will begin to talk about fronts, trying to understand the formation of fronts, and we want to understand the formation of the front regardless of the dynamics for now. So this process is sometimes called kinematic frontogenesis. Kinematics means we're focusing on the motion for the sake of the motion. We're not going to get too deep into ageostrophic circulations and QG and forcings and whatnot. We're just trying to look at the mechanisms that lead to the intensification of the temperature gradient. And so there's a function called the frontogenesis function. I wrote it here. This was introduced by Pedersen, and you'll remember Pedersen by the Sutcliffe-Pedersen mechanism. So back in the 60s, this is by definition simply the time derivative, and notice that this is a total or Lagrangian derivative of the gradient of theta. Okay, horizontal gradient of theta, d dt. I believe this is a 3D gradient of theta, not just the horizontal gradient. No, the horizontal potential temperature gradient. Okay. Horizontal potential temperature gradient of theta over here. This is great because it's good to have a definition, right? And also notice that this doesn't have to do with the intensity, but this has to do with the change in the intensity of the front. The intensity may be measured by the absolute value of the temperature gradient, like we're showing here, but here we care about frontogenesis, so we care about the growth of the front. And also, without loss of generality, we can always rotate our axes of coordinates such that the new x direction is along the front and the y direction is across the front. And so if we consider a front like this, for example, let's take a cold front. Let's go in this position. The new x direction, instead of being Cartesian x like this and y like this, we rotate by about, 70 degrees, 80 degrees. The new x direction here would be along this direction, and the y would be along this direction. And so u will be wind along the front, and v will be wind across the front. So no more zonal and meridional. So if you do that, then you can develop this derivative. Also, the gradient obviously simplifies because the gradient only exists across the front by definition, and so it's only going to have the d theta dy component, and there's a minus because if we think about a cold front, we are assuming that the y-axis points towards lower values of theta, and so if we think about a cold front, this definition is such that positive values of the frontogenesis function means a strengthening of the front. So this derivative, you can play around a bit with the math, and you can show that it has 4 different terms. The first is called shearing, with confluence, tilting, and the diabatic term. I'll let you absorb them a little bit. Maybe you can hit pause and just look at these terms, write them down, think really hard about them and what they mean. Let's start to examine the shearing term. Now, shearing term, d theta dx, du dy. Okay, let's keep that in mind. Let's imagine a situation like this one, where we have a cold front over here, warm front over here. Probably there are some cyclones, some low-level cyclone that is intensifying over here. And the x-axis is directed in this direction, and the y-axis in this direction over here. Notice the shape of the isotherms. So we have a pretty warm isotherm over here, 30 degrees, 25, 20, 15, and so forth. And here we have 15, 10, 5 Celsius degrees. So there is a d theta dx. Theta, both in the warmer area and in the colder sector of the front, are changing. Here they are decreasing with x, and in both cases they are decreasing with x, from pretty high values to lower, and from lukewarm, let's say, to cold. So d theta dx here is non-zero. Now let's examine u. U is the wind along the front, and here we're assuming that u is blowing in this direction, and here it's blowing in this direction. So this causes warm advection over here and cold advection over here. So what do you think the wind will do to these isotherms? The wind is going to push warmer and warmer air in this direction and colder air down here. So it will cause a packing up of the isotherms more and more and more. So you can see that intuitively this is going to cause a strengthening of the front. And u is going in this direction here, and if you change position in the y coordinate, it's shifting direction. So du dy is also non-zero, and so the shearing term here is non-zero, and it corresponds to this idea of the wind blowing air of different temperatures. Notice that if u had been in the same direction here and here, because of how the isotherms are stacked up, it would have caused a warming over here, but also a warming over here. So potentially it would have done absolutely nothing to the front. Okay, and the winds along the front can also act in a frontolytical way. So they can also act to kill the front. So examine the warm sector over here, and imagine that you have some wind that is blowing in this direction and a wind that is blowing in this direction. Now the d theta dx now is doing the opposite, because here theta is decreasing, but here it is increasing. So d theta dx flips signs in these two directions, and u also flips signs. So here you're going to blow up warm air, so here it's getting warmer, but also here you're going to blow down warm air, so these warmer isotherms are going to come down, and so this is going to cause a weakening of the front over here. So this shearing term, you have to be very careful, because it can also act to destroy the front. Okay, next up is the confluence term, and we could look at it here, d theta dy and dv dy. So now it's the across front velocity that matters, not the along front one. And consider a situation like this one, where we have some kind of a stationary front. When you have cold, warm, it means the front is stationary, it's not going anywhere. And assume that you have wind that is going on this side, it's going in this way, and this side the wind is going in, in the opposite way. And you also have isotherms that are packed over here. If the wind is blowing in this way and there is some kind of confluence over here, this will cause a convergence of the isotherms over here along the front. So this will cause a strengthening of the front. And this term is important because if you do some scale analysis, you can show that this is actually often an order of magnitude greater than the shearing term. So this is a very important term. Next up is the tilting term. And imagine that you have, as is often the case, some sloped isotropes over here. So you have a cold region over here and a warm region over here. And imagine that for whatever reason, you have cold air that is ascending here and warm air that is descending here. This is what is known as a thermally indirect circulation, because thermodynamics will have you do the opposite. Will have you go up in the warm and down in the cold. But there are cases in which the tilting term, in which thermally indirect circulations could happen. This could be the case, for example, during if there's significant topography, okay, or this situation is also observed in the exit region of a jet streak, okay, and in that case you have differential vertical advection of isentrope fields, and that leads precisely to this situation. Now imagine something like this where you have cold air that is going up. These isentropes are going to be packed up over here, and the opposite is going to happen over here. So this is going to cause a sharpening of the front. More and more isentropes are going to be packed across one single line over here, and so this will cause an intensification of the front. So this was d theta dp, so this is the slope, and d omega dy, so this is the ascending motion that has to be a differential ascending motion. So up over here and down over here. Fourth, last but not least, there's this term that is the diabatic term, and notice that here the derivative, the time derivative and the y derivative have been flipped, and so now this is the differential diabatic heating or cooling. So imagine a situation where you have a cold front. And the cold front, well, it's cold, and it's typically associated with clouds and rain. So below the front, there's typically a pretty thick cloud deck. So solar radiation is not going to go through in this region. But on the other hand, ahead of the front, you often have pretty warm conditions. So the sun can shines on the surface, the solar rays are absorbed, and they are re-emitted as sensible heat flux, partially a sensible heat flux, also as latent heat fluxes, of course, but sensible heat flux. And sensible heat flux will warm up the air around here. And so if you had a temperature difference, if both regions were to warm at the same pace, then nothing would happen. You'll be okay. But if the region to the east is warming and the region to the west is remaining the same, then the front is going to intensify. The temperature gradient is going to intensify. And this is but one example, and there can be many others. And this is an example of differential diabatic heating that acts to intensify the front. At night, you might think that the opposite happens because now the soil can cool down, and so maybe the front will become less intense at night. So this is one example of variations that happen during the day. So daily variations of the front. Okay. An example is given here by this front that is moving. This is November 2007, and here we're showing again this cold front that is being drawn over here, and we're showing 1000 hectopascal equivalent potential temperature in black contours and sea level pressure in red contours, and we have different time, November 15, 16, 12 hours later, November 16, and 12 hours later is November 17. Now, what I want you to pay attention to is this area over here where we have the front. You can see the isotropes here pretty packed together, and as these move over the Gulf, and where you'd have pretty warm oceans over here, ocean temperatures over here, you can see that these isotropes suddenly get spaced out quite substantially. Okay, so pretty packed. And as you go over the ocean, and this probably doesn't have to do with the diurnal cycle of insolation, but nevertheless, it's diabatic in the sense that you have these really strong fluxes of temperature that come from pretty warm ocean. Okay. Now here we're providing some simple, 1D pictures, if you will. This slide is just to invite you to pay attention to the fact that in real life fronts are much more complicated, and so you really have to think about 2D structures. You have to think about the frontogenesis and frontalysis, or frontalysis, where's the accent? I don't know. The creation or the destruction of the front is a function of, first of all, the tilt of the isotropes, but also how the axis of dilation that now becomes an important component of the 2D flow, how that is oriented with respect to the isotrope. So you might have cases where the axis of dilation acts to space out the isotropes, and you might have cases where maybe very little happens, right? Because maybe there isn't so much motion, and you have cases where there's motion only in this direction but not in this direction, and so forth. In this case, if you have them spaced out vertically, you have dilation over here, so the front is getting spaced out, so it's weakening. But here in this, convergence point, if your isotropes are oriented 90 degrees, flip 90 degrees, then you have a tightening of the front over here. And here I wanted to present you with examples of the frontogenesis function. And here we're looking at shear and confluence terms in particular. And you can see these are different cases. These are different cases, obviously. So we have one in the East Coast, a couple on the East Coast, and one on the Pacific. And, just showing, in this case, there's pretty strong frontogenesis ahead of the front, and here, right behind the cold front, and something similar. Also here, right behind the cold front, pretty substantial. And what else did I want to say? Here you can see the winds that are blowing in this direction, and so probably acting to potentially strengthen the front, maybe aided with winds that are coming in this direction. Okay, well, let's talk about the dynamics. The dynamics are complicated because, as we said, they're complicated for a couple of reasons. First of all, we expect some ageostrophic circulation here. How do we know that? Well, because these are areas of pretty sharp, fronts by definition are areas of pretty sharp thermal contrasts. Whenever you have sharp thermal contrasts, you would expect pretty substantial thermal wind. But then thermal wind balance, for arguments similar to what we had discussed back when we talked about QG approximation, thermal wind balance will likely get disrupted, and in order for this balance to be restored, then an ageostrophic circulation will have to be formed. So something very similar happens with fronts, and so fronts are areas of substantial ageostrophic circulation. The kinematic formulation that we gave so far is a great description to look at some mechanisms that lead to the intensification or the demise of a front, but it doesn't really tell us much about this secondary ageostrophic circulation. Okay, and also we're kind of on our own because, as we said, the Rossby number now is a bit too high, and we can't really rely on QG here. Okay. All right, so the way that we are gonna go about this is by going back to the whiteboard and thinking about the equations of motion. We're gonna start with the simple Boussinesq approximation, okay? And we're going to forget about friction, obviously. And we're still going to be in a front relative coordinate system, right, as we did before. So U is along the front and V is across the front. We're still going to define geostrophic wind in a similar way as we had before. Phi is a geopotential. It's a geopotential function that we can use to define the geostrophic winds, excuse me. And we're also going to work with buoyancy instead of, so phi is over here, B is the buoyancy function. Okay, we're going to work with buoyancy. Okay, so we rewrite the equations of motion. And we also add a thermodynamic and a continuity equation. So this is, good old thermodynamic equation where n is the n square is the Brunt-Weisshaller frequency. So it's a measure of the stability of the atmosphere. This, we know it's the mass continuity. And we can always break the mass continuity equation in a geostrophic and an ageostrophic component, right? And the ageostrophic is going to be related to the vertical velocity. Okay, this we remember. We assume that the ageostrophic along front component is negligible, so it's just across front and W, and we want to be able to find a function that helps us describe W, so the vertical velocity and the ageostrophic component. Okay, so this strategy is to play a little bit with the along front geostrophic wind and with buoyancy, and we rewrite them, we expand. So if we go back here, we had this one for the geostrophic wind and we had the buoyancy equation, and these are made a mess. The total, notice the total derivative here and here, so we can just expand the total derivatives, and we assume that there's, we separate the geostrophic and the ageostrophic component. So here I'm just writing out the various terms, so nothing particularly complicated. And then I'm going to do a trick, and I'm going to take the y derivative of the buoyancy equation and the z derivative of the UG equation and multiply it by the Coriolis parameter. Okay, and why that is important will be obvious in a moment. And you do the math, or you can trust me, and you'll get, in the first case, you get something like this, and you get something like that. Now, the cross-front flow is going to satisfy a thermal wind balance condition, okay? And, sorry, this is the along front flow, my mistake. Excuse me. The along front flow has to be, there has to be a thermal wind balance, okay? And this thermal wind balance, you can, it was correct before. I'm so sorry. Cross-front flow is not geostrophic. It has an ageostrophic component, and there has to be a thermal wind balance. And the thermal wind balance is between the gradient in buoyancy and the geostrophic component of the along front flow. And so you can see that you can simply, if this is true, then the time derivative of this is also true. And so these two have to be equal. Okay, and the strategy is that if we equate these terms, maybe we're able to come up with an equation for the VAG and for W, who are hiding around here. If you do all the math, it turns out that you can define a string function, an ageostrophic string function. This is very similar to how we defined the geostrophic wind components as a function of the geopotential. And if you do that, then that equation simply becomes this very quote-unquote simple equation for the string function. And on the right-hand side, there's a q term that is reminiscent of the q vector that we saw when we talked about QG equations. Okay, this is called the Sawyer-Eliason equation, and it's an equation that, once we know the forcing term over here, allows us to write this 2D string function that describes the ageostrophic circulation along the front. Okay, so notice these terms, dug dy, d theta prime dx, and dv dy, d theta dx. So we could think about this term over here, and we can think about, let me hide this for a moment, we can think about a situation like this where we have these isotherms, isentropes, okay, over here. This is the y direction, this is the x direction, and these are the winds. And so notice that by definition of Q, the only term that is contributing to this is the d theta dy, right? Because dx dy, d theta dx is 0. dv dy is some value and it's not 0. And this means that there's a forcing over here. And here the Q arrows, these arrows represent the Q vector, that is the forcing term. And it can also be shown that the Q vector is 0 over here, where there are these black dots, okay? And so there's convergence over here in the warmer sector and divergence over here. So that means, very similarly to when we talked about the QG part, then there's going to be ascent over here and descent over here. And so this is the warm sector, this is the cold sector. So this is the warm part, this is the cold part. This is what the ageostrophic circulation is going to look like. Right, from the cold sector, there's going to be an ageostrophic component that is going to rise up and is going to go and is going to descend behind the cold front. Now, it's interesting because when the front intensifies, this is going to bring the isentropes even closer together, and so this circulation is also going to intensify. The intensification of the front leads to an increase of d theta dy, and so this leads to a strengthening of this circulation. And it's interesting because the front intensifies at the surface, but the question one might ask, why isn't this ageostrophic circulation, why isn't it doing anything to essentially kill the front, to contrast the front? Well, the answer is that when this is intensifying at the surface, these vertical velocities are not really strong at the surface, and so there's really little that this ageostrophic circulation can do at the surface. Okay, so the intensification leads to a strengthening of the front, but there isn't really, and there's almost like a sort of a feedback in a sense, but the ageostrophic circulation is not enough to contrast this feedback. Okay, and this also helps us understand why the fronts are so strong at the surface, and they are weaker aloft, because aloft vertical velocities are non-zero, and so something can be done to contrast the front. But at the surface, really not so much. Also, another important thing, the Coriolis torque can also be important both on the upper and the lower branches. And sometimes this can cause, depending on the orientation of the front, this can also cause a strengthening of the shear in the along front direction, which can, again, intensify via thermal wind balance, could potentially intensify the front. So the Coriolis force is not to be forgotten. Okay, so this is an example of a front over here, and this is, again, someday in November 2008. This is the west coast of the of North America. It's a pretty decent front over here. Here it's just showing, it's just showing 10-meter wind barbs and 1,000 hectopascals isotropes. Here we have the 10-meter wind barb, sea level pressure, and we also have the frontogenesis function. And here we have frontogenesis by confluence, okay? And here we are looking at pretty much the same thing, but instead of having the wind barbs, here we have the Q vector. And here finally, again, it's a Q vector, but the red lines are, let me see, these are isotropes. I believe these are isotropes, and the shadings here are omega, okay? So notice these arrows over here. Oh, and I forgot, sorry, there's shearing frontogenesis on the warm side of the front and confluent frontogenesis over here. So two different mechanisms, and you can probably appreciate them if you look at the wind barbs and the orientation of the wind barbs. But anyway, notice the Q vectors, how strong they are over here and how they're converging on this side over here. And if you compare this with this, you notice negative omega over here and positive omega over here. So ascent over here and descent over here. Take a cross section, look at what it looks like. This is, the black lines are isotropes and the shadings are velocity. So here you have really nice ascent ahead of the front and descent behind the front. Okay, so this is it's a little bit complex, but it's pretty much all we have to say about the dynamics. What kind of fronts can we usually encounter in nature? Well, I'm sure that the two basic definitions and distinctions you have already heard. The first one is the cold front, which is what I always think about when I think about fronts. And cold fronts are characterized by the advance of cold air masses with time. These are really important because they very often cause severe weather. And during summer, these can be storms, and during the winter, these can be, like significant snowfall, for example. And there are two kinds of fronts, which we never talk about. We rarely talk about, but there are two kinds of fronts. One is called catafront, and the other one is called anafront. And a bit like katabatic and anabatic winds. Katabatic, the prefix kata comes from Greek and suggests something like descent, and ana suggests something like ascent. So anabatic winds go up and katabatic winds go down, and something similar happens here. Cold fronts that have a katabatic structure, a catafront structure, essentially you have air, but the air doesn't ascend over the cold front. It is, there's no ascent in the warm conveyor belt, and typically they live aloft. Often they're characterized by cold and dry air that is pushing the front. And so they're not really associated with terribly severe weather very often. And so light precipitation is typically what these are accompanied by. And we have an example here. So this is a cold front aloft that is advancing. It's cleaning up the precip over here, but you see that it's not really doing much. There's a little bit of rainfall. And this is an example of a catafront over here. You see that it just goes like this. And this is from December 2002. And this is radar reflectivity. So this shows the rainfall. The rainfall is pretty modest, to be honest. And the other one is the anafront. And if you look at this animation, the anafront just goes above in the cold sector. And you can also see it here. It just, goes with no problem, goes towards the cold side of the front. And the precipitation often falls in the cold sector of the front. And so during the winter, these might be accompanied by, significant snowfall. And they're also, because the rain falls here and rain evaporates, this is going to cause a descending motion over here. So sometimes these are accompanied by a low-level jet and the surface that is pushing down. Okay, and these tend to appear later in the life cycle of fronts. We also have warm fronts, of course. If we have cold fronts, we must have warm fronts. Otherwise, why make the distinction? These are different, and they typically live. The warm air is lighter than dry air, than cold air, and so it lives aloft. And they essentially work by mixing. So they don't. It's not so much the lifting of the air like cold fronts might do, but it's the fact that they cause mixing of the air aloft with air at lower altitudes, and this might lead to condensation and precipitation. So typically, these are characterized by light precip. Unlikely that these would be characterized by severe weather. And we see an example here where we have like this warm layer that has descended all the way down, and it meets pretty cold temperatures at the surface. And propagation of warm fronts is still very much debated and still not as well understood as cold fronts. And then we also have occluded fronts. Occluded fronts typically happen in the later stages of extratropical cyclones. And these happen typically when either cold fronts overtake warm fronts or vice versa. If we have a situation in which warm fronts overtake cold fronts. And depending on how exactly it might happen, this leads to different features of the occluded cyclone. These are sketches of the life cycle of a maritime cyclone, and these are depiction of streamlines and isotherms, and this comes from an older paper by Shapiro and Kaiser that first proposed how these proposed a cyclone, a frontal cyclone model, conceptual model for these cyclones. And you see over here, there's a cyclone, there's a cold front, there's a warm front over here, and you see that the cold fronts typically move pretty fast, faster than warm fronts. This overtakes the warm front, and it causes this occluded area over here. And finally, we can also have coastal fronts, and we do have coastal fronts because, well, there could simply be that air has different properties, and air over the land is, for example, really cold, and over the ocean is really warm or really moist, and so there can be differences over the coast, and breezes and synoptic scale flows can clash and cause these different boundaries to be created along the coast. So they're often pretty shallow, they're quasi-stationary, and they tend to have a warm frontal structure. They're often, because they're stationary, and stationary fronts are usually a good breeding ground for cyclones, these fronts often are regions of significant cyclogenesis, and sometimes can also be accompanied by severe weather. Okay, so this concludes what I had to say about cold fronts. Thank you very much for listening, and I'll be happy to take any questions in class via emails or in any other way that you want to contact me. Thank you.